Hey guys, Kenna here. So, welcome to physics, and today we are going to be having a discussion about the nature of physics. So, what kind of things are we talking about here? So, we're going to look at this concept known as COMPT, CONPTT, and I'd really hope you keep this at the back of your mind for the rest of the year as we go through physics, because it helps us to evaluate how scientific a statement or idea is. And so we're going to look at exactly how that works today, and hopefully you'll be able to use it and apply it in the future. Number two, what role does serendipity play in science? Science is often looked at as a very concrete, numbers-based, fact-based thing. Uh, so it may seem like there's no room for luck in physics, but there is a room for luck in physics. And if we make good observations, that luck can turn into some great discoveries, and we can talk about that a little bit today. And then lastly, what is the value of skepticism and how is it related to pseudoscience? And if you notice your parts of your speech, pseudo, that prefix, means false. Okay, so keep that in mind as we go ahead and do it. All right, so let's jump right in. First thing we need to do is kind of think about what it is we're talking about. When we go ahead and say a vocabulary term, we want to make sure that we're thinking of the same thing, that when we use it, we're using it the same way. The first term we should probably use, which is an interesting one to define here because you've probably been having science class since your middle school years and you kind of have an idea of what it means. But if I were to ask you particularly exactly what science is, you'd probably struggle a little bit about coming up with a textbook definition, so to speak. So here we go. Science is the systematic observation of natural events and conditions in order to discover facts about them and to formulate laws and principles based on these facts. Okay, this will tie into COMPT that we'll talk about here in a little bit, but we really want to use science as a system of how we approach problems, about how we analyze situations and come to conclusions. Now, for most of you, when you think of science, you think of a science class, or you think of it as a thing that is, or a thing that you can get somewhere. But I really want you to focus on science as a way of thinking. And while many of the definitions that you will hear of science deal with knowledge, how much you know, how well you know it, how detailed your understanding of it, we're going to focus much more in this course on the process of how you do science. Okay, the process by which we obtain knowledge. I was a huge fan of the late astronomer and humanitarian Carl Sagan, and he once said, science is a way of thinking much more than it is a body of knowledge. And that's really how I'd like you guys to go ahead and approach physics as well as science in general. Think of it as a tool that you can use to be better informed and better prepared to make decisions in your own life. Okay, you can use this process to go ahead and help you evaluate pros and cons of situations, everything from choosing the college that you're going to go to, you know, whether or not you make decisions in your own personal life. Okay, all right, so let's start out by taking a look at COMPT, CONPTT. Science is consistent, it's observable, it's natural, it's predictable, it's testable, and it's tentative. So what do we mean when we say that science is all of those things? Science versus what? Well, we're going to really kind of keep it science versus, let's say, non-science. Okay, we don't want to give it a very specific term because that implies too much or applies bias to what we're talking about. Those things that are covered by science meet these criteria. Now, some of them may be more or less obvious, but I hope to go over them here so you can better understand exactly how they apply to what we're talking about here. So let's go ahead and begin with consistency, okay? Science is consistent because the results of repeated observations should occur reasonably the same way, whether performed or repeated by the same person or different people, as long as they're a competent investigator. As long as they can make good observations or using the appropriate tools and methodology, they can come to the same conclusion. Um, it's consistent in the fact that the event is also free from self-contradiction. It's consistent when you use it in multiple situations. If it doesn't apply to different situations, then it's not a very reliable tool, and therefore we have to examine why that occurred. And if we can't explain why that occurred, then we have this problem where it's not compatible within our observations. So the first thing we start looking at is it's consistent. So right now, I'd encourage you to go ahead and grab a big book that you have somewhere in the house, or at least something large and heavy. Now you pick it up off the ground and we're about to drop it. So what's going to happen when you drop it? Now, most of you probably said it's going to fall. Okay, let's try it. Let's go ahead and drop it. Okay, so it did, it fell. Okay, what if we do it again? What do you expect to happen? Right, you expect it to fall again. So let's try it again. Let's see what happens. Okay, yeah, it fell again. What if we did it another time? So pick the book up again. So when we drop it, what's going to happen? You would expect it to go ahead and fall again to the ground. What if this time, however, you dropped it and it just floated there? Okay. The previous observation of it repeatedly dropping is very consistent. That's very scientific. But if it starts to float like that, you need to come up with some explanation as to why it floats. Otherwise, you lose consistency in your observations. Okay, so maybe there's strong wind blowing up or something like that, or it's suspended by a fishing line or something that's keeping it from falling. But if you can't explain why it did that, okay, as you're sitting there having your matrix moment, we have just moved out of the realm of science. Okay. Number two, observability. How did you know that the book fell? Well, if you're holding it, you probably saw it happen. But maybe if you closed your eyes and drop it, would you still know it happened? You probably would. You'd hear it. You'd feel maybe the wind as it blew by you. Okay. Observation is not limited to just what we can see with the eyes. Okay. Observation is when we have an event that we're observing. Okay. We can see that it's happening using some extension of our senses. Okay. When we use a microscope, we're looking smaller, but we're using vision. When we use a telescope, we're looking farther, but we're using our vision. When we go ahead and use a sense of smell, when we go ahead and use a sense of touch, maybe something like a Geiger counter, right? Measures radiation. We can't feel that on our skin, but we have tools to extend the ability of these senses to detect. If a phenomenon cannot be reproduced through controlled conditions, natural evidence of the event's occurrence must be available for us to investigate. We have to be able to find a way to go ahead and figure out what's going on. Now, this next one is one that a lot of people get tripped up on, and so that's what we want to take a look at, and that's natural. When I say natural, natural versus what? What's the first thing that pops in your mind? Now, many of you would probably say natural versus man-made. Yeah, that's a common response we get. But what is man-made? If you think about the desk that you're sitting at or table that you're sitting at, if you think about the clothes that you're wearing, if you think about the chair that you're even sitting in, what's it made of? It's made up of matter. It's made up of atoms. It's made up of everything that's the same stuff as everything else. So that's still natural. We have reconfigured it, but it's still natural and behaves according to the laws of physics. Okay. When I say natural here, I'm saying natural versus supernatural. Scientists are not allowed to go ahead and use supernatural explanations because you cannot, and we'll see this later, test them. You can't show using evidence and our senses or make observations of these things happening. So when we say natural, we're saying something that can be explained without saying it was a ghost. God did it, right? Can you show evidence that that's true? Maybe someday we could, but at this current time, we have no way to measure or quantify that or to show evidence that it's happening because of that. And as such, it lies outside of the realm of science. So scientists must be able to conduct controlled experiments in which they have designed the intervention of a supreme being. Could you go ahead and say the supreme being did this one, but not this one? Well, you can't really tell God, okay, God, don't do this one, don't do, but go ahead and do this one, because we can't independently observe and test it. It falls outside of the realm of science. And this one's always a little tricky because everybody likes to pit science versus religion against each other, when in reality, most of what they cover does not overlap. Okay. Science only deals with those things that we can quantify and observe and experiment on. Those things that are outside of that end up kind of falling into this realm of what we'll call theoretical, okay? If in science at all. And we'll talk a little bit more about that later. The next one is predictability, okay? In predictability, we picked up that book. Do you remember picking up that book? And we dropped it. And what happened? Okay, yeah, it fell. And we picked it up and we dropped it again. And what happened? It fell again. The next time we picked it up, we predicted that it would fall again. Science is only as good as its ability to predict events. The reliability of those predictions can be really tricky sometimes if we think about like predicting the weather. If you live in Southern California, it may be a lot easier to predict the weather than it is in Oregon, where it changes much more often. Okay, it's going to rain today. No, it's not. It's going to snow today. No, it's not. These kind of things, because of small little variations, can cause some huge ramifications. And we'll talk more about this later in the semester as we start looking at these complex variables. Okay. The next one is testability, and this is probably one of the pieces that you're most familiar with. We have to be able to test it. Now, that's a little trickier than you might at first glance think. There are lots of things that we think of as being very scientific that push this boundary a little bit. Now, how many of you have heard of a black hole? Okay, so what's a black hole? Now, as you're coming up with a description of what it is from some television show you saw or some class where you had a discussion about it, how do we know that? Okay, we can see some evidence of what it does, how it impacts things around it. But there's a part of the black hole called the event horizon. And we have no idea what's on the inside of that. Okay, no idea. Science has no evidence because everything that crosses it is gone as far as we know, and nothing ever comes back. We can't send a satellite to it or some deep space probe to evaluate it because there's nothing to evaluate. And if it were to cross the event horizon, you're not ever getting it back, including a signal from it. You couldn't beam out information to learn about it. I mean, when we start looking at this, is that really science? We cannot use our observations to go ahead and understand what's inside the event horizon. It's not at current time testable. Will it be at any point in the future? Who knows? But for the longest time, there were other things like Einstein's theory of relativity, right? Uh, it could not be tested. And so at the time, it was what we called theoretical science. And until our technology improved and we could find a way to test it, it stayed in this kind of fuzzy realm of, yeah, science, but not really science because we couldn't test it. So CONPTT, right? This is the first of the two T's. Science is testable. And if you can't test it, it's not really science. So what is in a black hole? There's a beautiful representation of it in the movie Interstellar, if any of you have seen it. It's actually as close as science really can predict, but science doesn't know in this case because it's not testable. And so when we take a look at this, we have to keep that in mind. This is probably one of the more concrete pieces that we need to keep in mind. And the last T is tentative. So what's tentative? Anybody know? Okay, so tentative means not set in stone. If I were to say that Carolyn and I have a tentative plan to go out for coffee after this, okay, is it going to happen? Maybe, maybe not. It's tentative, meaning not set in stone. It could happen, but it could be revised. Now, this has happened a lot more in science than we think. Okay, all right. So we all know the Earth is flat, right? No? Really? Well, for the greater part of human history, that is what we believed. Okay, so the Earth's not flat, but at least we're at the center of the universe, right? What? We're not? Okay. Well, now we have discovered that we are not even at the center of our own solar system, let alone the universe. But for most of human history, that is what we believed. How did we discover that this was incorrect? As technology improved, we tested these ideas. And as we made observations and got in new data, we changed what science understood. To me, this is probably the most powerful piece of Compt. Okay, so many people see science as very rigid and fact-based, which is good because there's evidence, there's data, there's numbers to go ahead and support whatever it is we're saying. But one of the biggest strengths in my mind of science is that as we learn more, we adjust it to reflect that. Science is not set in stone, so what we thought hundreds of years ago, we don't have to believe in that still because the evidence no longer supports that idea. It may have been a good idea at the time, but science grows, science adjusts, science reflects changes in our understanding about the world around us. Okay? So we have now gone through all of the different criteria. We recognize these 6 criteria as what defines science. It's consistent, observable, natural, predictable, testable, and tentative. Here's a good acronym to help you remember it. CONPTT, C-O-N-P-T-T. If we go back to that idea of science being very rigid and very structured and set in stone, it may feel like everything is planned out and we know all of it. But in reality, we actually have a lot of luck. Now, luck alone won't get you there, okay? But this is where we prefer in science to use the term serendipity, okay? Sometimes a discovery is made because of luck or a hunch or a new way of looking at the world, and we call this serendipity. Now, this is luck with great observations, okay? Putting together patterns and relationships and being able to draw conclusions from it that you can use as a prediction. Champagne is a great example of serendipity. For most of its history, champagne was still and red. It's the sparkling white version of champagne that's most widely known. But this version of champagne was a complete mistake due to a poor grape growing conditions and cooler winters that caused the yeast to go dormant. Now, what happened? They kept it in a cave, they kept it going for a while, and when they finally got back to it and tried to see what happened, it had fermented and become sparkling. Okay? That's what gives you the pop when you take off the cork of it. Okay? Champagne is a great example of serendipity in science, but if they hadn't observed it, if they hadn't tried to figure out what caused it, we may not have it today. So it's the serendipity is the combination of luck and preparedness. You know, the Boy Scouts always talk about luck favors the well prepared. Well, science favors the well prepared as well. Okay. And serendipity is a reflection of that. Now, this is another good example. Why do I use champagne? Well, because when we think of champagne, we don't think of scientists in lab coats. Okay? Science is not just for scientists. There is a huge amount of value to each and every person on this planet if they can think logically and they can think skeptically. Don't trust what somebody else says, and that includes me. If you're unsure, if you don't feel like the evidence is there to support what somebody is saying, challenge it. Doesn't mean you have to be rude about it, but don't accept it just because somebody said it. Ask questions, look for evidence, be skeptical. If science is to have any real benefits for the developing world, and many scientists think it can, we, as people, need a much broader understanding of what science is, how it operates, and its role in society. Remember, I was talking earlier about the idea of science as a way of thinking. If we use that CONPTT tool to evaluate statements, we are going to better understand the meaning of that statement and its validity and use our judgment and logic to make better decisions. Now, all of the things that we've talked about are science general. Now I'd like to kind of zoom in and focus a little bit more on physics in particular. Physics is another thing that people think, oh, rocket science is really complicated. And there are parts of it that are, I'm not going to lie to you. But in general, physics is just the analysis of nature. We do a systematic evaluation of the way the world behaves around us. And this includes the studies of matter, its motion through space and time, along with concepts such as energy and force, things that we actually deal with on a day-to-day basis. We may not name all of them, but these are the things that we do. And when we're studying physics, we're still going to go ahead and follow the scientific method. Now, I hope you realize at this point that there aren't set 7 steps to the scientific method. I mean, it's tempting to say that there are because it makes it really easy for us to remember and to vomit it back at somebody on the test. But in reality, these have to be flexible. They're general guidelines for how to conduct an experiment, or if we're thinking about science as a way of thinking, they're a series of steps that can help us evaluate what it is we're exploring, whether that's a scientific concept. We talked about black holes earlier, why the book is floating if we drop it and it doesn't fall. Or maybe we're going to use it to decide whether to take the bus or ride a bike to school. We're going to use it when we decide to make a decision to go to a party or not go to a party. We think about weighing the pros and the cons of a decision. What's the problem? What information can we gather on it? What are the likely outcomes? And then we go ahead and make a decision and we kind of figure out if that decision was a good one or not based on what the conclusion is or the outcomes. All right. Science, unfortunately, is not always as predictable because we don't understand all the variables and how they relate to each other. When we use the scientific method, not all of the steps are always going to be completed, or they're not completed in order, or some of them are not completed at all. How could you use the scientific method we had on the previous slide to fix a bicycle? How would you use it to choose a college to attend? Pause the video here, take a minute, and think about these 2 scenarios and how you could apply COMPT, the scientific method, to evaluate these situations and to help you better understand how to solve these problems. Pause the video here. Well, welcome back. Okay. What'd you figure out? Did you come to a good conclusion? Hopefully you recognize that the scientific method is a tool. Okay. It allows us to logically evaluate the options in any particular situation and help give us an idea of what the outcomes may be. All right, now there are a couple other things that I want to review that if you guys took freshman physical science, you may remember. And so let's evaluate some of these other concepts and terms. What is the difference between quantitative and qualitative? Well, a big part of it is in the name. Quantitative deals with quantities. These are things that are numbered, versus qualitative says quality in it. These are descriptions where we're describing things. They both can be valuable. In physics, we prefer quantitative because this gives us something to compare because we're looking at numbers. The next one is correlation versus causation. A correlation is a mutual relationship between two or more things. Causation is where one event directly causes the other to occur. Okay. Now, if we think about causation, okay, if I put an ice cube out on a hot summer's day, it melts. The heat from the sun caused the ice cube to melt. That's causation. Let's try another statement. In summer, the amount of ice cream sold goes up. Also in summer, the number of murders goes up. Therefore, because we sell more ice cream, there are more murders. Now, there is a mutual relationship there. In summer, both things go up, the number of murders and the number of ice cream sold. But selling ice cream does not cause murder. At least no evidence that I have found suggests so. Whereas we can consistently, remember COMPT, see that there is a direct connection between the heat of the sun and the melting of the ice cube. Which leads me to this idea of skepticism. Now, I hope every single one of you is a skeptic. I hope you have a questioning attitude towards any knowledge, facts, opinions, or beliefs stated as it facts. Don't take it just because somebody said it. Ask questions, evaluate the evidence before you just accept with blind faith. Now, most scientists, being natural skeptics, test the reliability of certain kinds of claims by subjecting them to this systematic investigation, which we call experimentation, some form of the scientific method. Why do we do this? We want to show with evidence that something is factual. If there is no evidence, science rejects it as complete falsehoods or what we would typically call pseudoscience. Pseudoscience is a set of ideas based on theories put forth as scientific or put forth as evidence-based when they're actually not. Look for the evidence, look for the data. If it's not there, we must reject it. Okay? And even if you don't like it, if the evidence is there, we need to accept it. So rather than there being this big war between science and religion, like a lot of people like to put forth, I would argue that a better distinction is a war between science and pseudoscience. But even this gets fuzzy, okay? The line between science and pseudoscience is notoriously loaded with definitional disagreements. The categories of what's real science versus non-science are too broad and fuzzy at the very edges. And so sometimes you'll see people applying the term pseudoscience to science that they don't want to accept, which reflects a certain amount of bias. Some pseudoscientific theories are based on an authoritative text rather than on actual data. And so you need to keep in mind, where is your evidence coming from? How valid is the source? And so in science, the numbers need to be clear as to where they came from. A result that is come to by, say, my 7-year-old son is probably less reliable than the result attained by an established scientist who has many discoveries under their belt. Okay. Another problem with a lot of pseudoscientific theories is that they can't be tested because they're so vague or malleable that anything relevant can be kind of fit in to validate, if you will, that theory. I always loved this quote from Einstein. Einstein once said, "No amount of experimentation can ever prove me right, but a single experiment can prove me wrong." That's a powerful statement. Science is only as good as the results it gets us. If the results are not panning out, we need to reevaluate our statements, re-experiment, and look for a new explanation. But even that becomes tricky because, as John Muir said, when you try to change any single thing, you find that it's hitched to everything else in the universe. And it's a big universe. And we understand so much about just our little corner. We can try and apply it to everything else, and it seems to work in certain circumstances and in others not as well. Now, I wanted to leave you today with an example of this in play. Um, Science is a tool, and I hope you'll treat it that way. By its very nature, it's not good, it's not bad, it just is. The famous scientist Richard Feynman was part of the Manhattan Project with Albert Einstein, Enrico Fermi, Robert Oppenheimer. And one of the things that they're responsible for is the development of the first atomic weapon. And looking back on that, this is a quote from Feynman, January 1988. "When I was younger, I thought science would make good things for everybody. It was obviously useful. It was good. During the war, I worked on the atomic bomb. This result of science was obviously a very serious matter. It represented the destruction of people." Now, that's a powerful thing. What is the impact of what you work on, right? Even if you have the best intentions, remember, science is not good or bad. Science is a tool that can be used for good or used for bad, depending on how we apply the tool, right? Hammer is great if you're trying to build a house from somebody, give them shelter. Hammer is not so great anymore if you use it as a weapon to hurt somebody. It's a tool, and how we use it is important. Okay. So, this concept of the implications of what we do, nothing exists in a vacuum. And we have to remember that. Okay. When we're thinking about the work of the Manhattan Project, like you can see here, that has serious ramifications. Now, I don't think any of the scientists that were working on it quite knew just how dangerous what they were doing was going to become. Let's continue on with the quote from Feynman. "After the war, I was very worried about the bomb. I didn't know what the future was going to look like, and I certainly wasn't anywhere near sure that we would last until now. Therefore, one question was, is there some evil involved in science? Put another way, what is the value of the science I had dedicated myself to, the thing I loved, when I saw what terrible things it could do?" It was a question I had to answer. So remember, as we continue through this course, I hope you will see science as a tool, but I hope you'll be skeptical. Don't take things just because somebody, including me, says them. Look for the evidence, evaluate it for its usability, its predictability, and think about everything is only as good as its ability to be used as a tool. Okay? Not inherently good, not inherently evil. Some of the things we as humans have done have been helpful, some have been hurtful. And it's how we apply them that makes them a valuable tool. Now, there's a companion reading to go along with today. What you should know about physics. I hope when you read through that, you'll kind of keep this that we've discussed here in mind. Feynman, COMPT, serendipity, skepticism, pseudoscience. What is the value in terms of what you're learning for the rest of your life? How can you use this as a tool to better your own pursuit of a better life for yourself? All right, guys. Thank you so much. I hope you have a great rest of your day. Take care of yourselves. I'll talk to you soon. So long. Bye bye.